of the video clips.
Now we know a couple of things to improve. In the end, this trip was excellent and we are happy with the result.
They found a ship and no one got lost. For Perty and the dive club, it's a huge win.
Now we have enough information to start planning what to do next. Probably we want to make a 3D model of the wreck so we could finally identify what wreck it is. This is the starting point.
Sir, shall we start, sir? Hello.
Chandan, you can start. I think we'll
Okay, sir. So, sir, kindly if you can unshare your screen so that I can proceed with the introduction part. Okay, thank you, sir. Sir, is the screen visible? Hello. Is the screen visible, sir?
Yes.
Okay. Good afternoon, everyone. We are once again back for our second session on the last day of our FDP program on sensor technology. So I wholeheartedly welcome one of our prominent faculty member from Department of Electronics and Communication Engineering, NIT Jamshedpur, Dr. Prasant Kumar among us. So good afternoon, sir. So Dr. Prasant Kumar, Faculty, Department of Electronic Communication Engineering, NIT Jamshedpur. He has completed his PhD in wireless communication from IIT Patna in 2016. His MTech in telecommunication engineering from NIT Durgapur in 2007. Bachelor in engineering in electronics and communication engineering from NIT Patna 2001. He is having more than 17 years of teaching experience from various NITs, universities and engineering colleges. His research area are smart sensor, wireless sensor monitoring, underwater acoustic sensor. He holds membership of various professional bodies across the country. He is the lifetime member of the Indian Society for Technical Education, New Delhi. Lifetime member of the Institute of Electronics and Telecommunication Engineering, Delhi. Senior member of Institution of Electrical and Electronics Engineering, IEEE, USA. And he is having more than 21 research articles with 167 citation, having H index of 7 and I10 index of 6 in his credit. So we are blessed to have him among us. And with this, I would like to request Dr. Prasant Kumar sir to proceed with his presentation.
Thank you, Chandan.
Thank you, sir. Thank you, sir.
A very warm good afternoon to all the participants. I'm here with my presentation on underwater sensors. So basically, I've chosen to give a presentation on sensors used in underwater wireless communication and their applications. This program is on sensor technology. Sensors are every day, everywhere, and we are using sensors every day. Sensors are in our pocket, in our surrounding, and in so many things, we just can't find a place where there is no sensor. And mainly the sensor technology has become so popular because of its counterpart, the wireless communication. As you all know that wireless communication,
Dr. Prashant.
As you all know that wireless communication has taken giant leap, and it has become very popular over the days. So Basically, I'm going to give a presentation on how wireless communication is used in underwater and what are the different sensors that are used underwater. So basically, the first thing I want to tell is why we want sensors underwater. The vastness of oceans mirror the vast potential that lie beneath it. In order for scientists, researchers to explore these vast resources, newer and better sensing technology is pertinent. Basically, this is the outline of my talk. First, I will talk about underwater acoustic communication. Then I'll talk about underwater communication using light. Then I'll move on to underwater sensor network for early warning generation. And finally, I'll conclude my talk with a very brief preview to Internet of Underwater Things. What is underwater communication? Underwater communication is a technique of sending and receiving message inside water. Electromagnetic waves are severely attenuated in saline water and require large. Sir?
सर आवाज कम आ रही है, आप उसको ईयरफोन को हटा के डायरेक्ट बोलिए ना, माइक से उसी में आवाज अच्छा, मेरा तो उसी टाइप का है। ओके सर, डायरेक्ट जो कैमरा माइक है उसी से आवाज सेंस हो रहा है। ओके सर, आई एम जस्ट डूइंग दैट, जस्ट होल्ड ऑन। आप अपना ईयरफोन हटा के डायरेक्ट उसमें बोलिए तो देखिए तो। एम आई ऑडिबल नाउ? या नाउ इट इज ओके। No. You are muted. Am I audible now? Yes. Okay, so I'll continue with my presentation. This much voice is sufficient. Okay, so underwater communication is basically the technique of sending and receiving message inside water. Electromagnetic waves are severely attenuated in saline water and require large antenna. At the same time, optical waves are affected by scattering and require high precision in pointing the narrow laser beams. So acoustic waves as the carrier is the best choice for underwater communication. Underwater acoustic communication basically is used in underwater sensor networks. Underwater sensor networks are used for surveillance, undersea exploration, pollution monitoring, video acquisition, etc. This is the architecture of underwater wireless communication. You can see that there are so many entities which include divers, crawling vehicles, swimming vehicles, seafloor data links, anchored underwater sensors, and many access points inside the water. The underwater acoustic channel is characterized by some very important points. The first being that it is a range-dependent communication system in which the bandwidth of the system depends on the range. If you want to communicate over a long distance, you will get a very narrow bandwidth. If you want to communicate over short distance, then you may get large bandwidth. As you can see in the diagram, there is a graph which shows that if you want to do communication over 10 kilometers, you will get a bandwidth of around 10 kilohertz. But if you want 100 kilometers, you will get a bandwidth of hardly 1 kilohertz. Then underwater communication suffers from time varying multipath, and there's a problem of low speed of sound which makes substantial delay in communication. It is said that the worst of terrestrial, mobile and satellite communication is there in underwater acoustic communication. In addition to that, there is a large transmission loss which includes energy spreading and absorption loss. There are noise which may be ambient noise or man-made noise. The underwater channel is characterized by multipath, which is generally formed by the reflection from the top and the bottom surface in case of shallow water, and due to ray bending in case of deep water. Underwater acoustic channel is modeled as an multipath channel in which there is time variant and correlated fading factor in the signal amplitude of the power accounts for multiplicative fluctuation of each individual path. Underwater channel has noise coming from variety of sources like cavitating shaped propellers or snapping streams. Underwater tests have shown that channels
often exhibit poorer behavior than a relay distributed channel. Underwater acoustic wireless sensor network. Basically, a number of sensors and vehicles are deployed to perform collaborative monitoring tasks over a given area underwater. Network which can adapt to the characteristic of ocean environment. Underwater multimedia acoustic sensor networks will enhance the applications like coastal and tactical surveillance, undersea explorations, pollution monitoring, scientific data recording at bottom stations, speech transmission between divers, video acquisition, disaster prevention, and equipment monitoring. Underwater acoustic sensor network communication architecture can be categorized in three heads: static two-dimensional underwater acoustic sensor network, static three-dimensional underwater acoustic sensor network, and three-dimensional network of autonomous underwater vehicles. These are shown in the figures you can see. Basically, whatever is underwater will have to use acoustic signal. What is above water can use radio waves or electromagnetic signals. This is the two-dimensional architecture in which we assume that the sensors are fixed at the floor of the sea at one level, whereas this is the 3D architecture in which the sensors are not fixed at the floor, they are having different heights, so it contributes to a 3D communication system in which the nodes are at different locations. This is a 3D architecture with underwater autonomous vehicles in which the nodes now are mobile, so there will be more Doppler spread and the system need to incorporate techniques to reduce the Doppler effect. This is a diagram in which underwater acoustic communication is demonstrated. There can be horizontal as well as vertical communication. Please bear in mind that horizontal communication has got lower bandwidth, whereas the vertical communication can have greater bandwidth. Problems with traditional underwater measurement. Because we are to talk about sensors that are used in underwater, we are now trying to move our focus on the sensors. In traditional approach, we deploy underwater sensing instruments, record data, recover the instrument, and then process the data. This approach has the following disadvantages. Real-time monitoring is not possible. No online system reconfiguration is there. Failures or misconfigurations cannot be detected before the instruments are recovered. The amount of data that can be recorded limited by the capacity of onboard storage device, that is the memory or the hard disk in the equipment. Challenges of underwater communication. Battery power is limited and usually batteries cannot be recharged because solar energy cannot be exploited. The available bandwidth is severely limited. Channel characteristics include long and variable propagation delays, multipath and fading problems, high bit error rate, and temporary loss of connectivity. Underwater sensors are prone to failures because of fouling and corrosion. A unique feature of underwater network is that the environment is constantly mobile, naturally causing the node passive mobility. System requirements. Simple control systems require low bit error rate and data rates are up to 1 kbps. Telemetry data requires a data rate of up to 10 kbps and a BR of 10 to the power -4. Speech signals require a data rate of 3 kbps and a bit rate of 10 to the power -2, whereas video transmission requires a data rate of 0.1 to 1 Mbps with a bit rate of 10 to the power -3. Please bear in mind that systems are improving, so video naturally requires a higher data rate because of the high resolution videos. So the requirements basically push the underwater communication system to develop new schemes, new techniques so that the data rate can be increased and the bit rate can be reduced. There are certain differences with terrestrial sensor networks like high power consumption, larger memory, higher cost, longer latency, and sparser deployment. Basically, if you look at the modulation techniques used in underwater acoustic communication, you will find that earlier it used to be single carrier system, but now we are using multi-carrier system, and different variants of OFDM is now being used over the last few years for underwater acoustic communication. Now we'll move to underwater acoustic communication using light. Underwater acoustic communication using light involves sending and receiving light and detecting objects and doing measurements. Application of underwater optical communication include diver-to-diver communication links, diver-to-submarine links, submarine to underwater autonomous vehicle links, submarine to submarine links, underwater vehicle to underwater autonomous vehicle links, submarine to satellite links. This is an example in which we saw how light can be used in underwater communication. You can see the preferred range of communication is from 300 to 700 nanometer. Generally, the 700 nanometer light is used. Free space optics is a line of sight link that utilizes laser or LEDs to make optical connection that can send and receive data information, voice and video through free space. Now applying free space optic concept to seawater, the transmitter receiver for an underwater link can be very similar to a free space optic link in air, the major difference being the wavelength of the operation. Ocean has widely varying optical properties depending on the location, time of day, organic and inorganic content, as well as temporal variations such as turbulence. Underwater attenuation is the loss of beam intensity due to intrinsic absorption by water, dissolved impurities, organic matter, and scattering from the water. And impurities include organic and inorganic particulates. As you can see in the diagram, that the absorption is generally lower in the range of 200 to 300 nanometer and beyond 700 nanometer. That is why 700 nanometer is preferred as the wavelength of operation. Scattering by pure water. Because of the inherent scattering of molecules and of the salts dissolved in water, a certain amount of initial scattering has to be taken into account before calculating the total scattering coefficient. This type of scattering is Rayleigh scattering, with a strong wavelength dependence seen with increased scattering at shorter wavelengths. Scattering in the ocean is due to both inorganic and organic particles floating within the water column, whereas in open ocean scattering comes mainly from organic particulates, the planktons and all other living organisms in the sea. Scattering from the particulates depend on the degree of external reflection and diffraction by the geometric form and internal reflection and reflection from the index of refraction from the particulates. High power LEDs are used for this. Recently, high power LEDs have been commercialized. As a possible future application, the possibility of using high power LED for underwater communication will be possible, where the desired wavelength of operation are between 450 to 550 nanometer. For optical communication purposes, the following aspects should be considered: optical wavelength, optical output power, reliability, beam parameters. Lumin LEDs are presently the industry leader in high-powered LEDs. They have focused on efficiently extracting light from the LED and the packaging the LEDs so that the heat can efficiently be removed. These are differences between conventional and popularly used LEDs in underwater communication. Now we'll move on to underwater sensor network based early warning system. There's an idea what is the meaning of early warning. Basically, early warning means we can detect something in advance, something which is catastrophic, which is dangerous. For example, if we could detect that an earthquake is going to happen or a tsunami is going to happen, we would be very lucky to save lives. So what is the problem statement in this early warning system? Basically, we are dealing with underwater communication, so we'll focus on tsunamis and earthquakes that generate the tsunamis. Tsunami is actually a series of ocean waves produced by earthquakes or underwater landslides that can travel at speeds averaging 450 miles per hour in the open ocean. A tsunami warning system, TWS, is used to detect tsunamis in advance and issue warnings to prevent loss of life and damage. The evolution of TWS shows a significant development from seismic centered to multi-sensor system architecture. We'll just look at how things have changed and how the sensors have changed the whole scenario. Two equally important components: a network of sensors to detect tsunami and a communication infrastructure to issue timely alarms to permit evacuation of coastal area. This presentation highlights the physical layer challenges in establishing a reliable, low power consuming and long life underwater wireless sensor network system for such early warning generation. Wireless sensor networks. We'll just have a very brief preview of what a wireless sensor network is and how it can be used in underwater acoustic sensor network and how that can be used for a tsunami early warning system. The elements of a wireless sensor network include a field, the region over which the wireless sensor network is deployed. The nodes contain sensors that collect information. They are not necessarily communicating at any particular time, can only communicate with a few nearby nodes, use routing protocols to convey to the base station in an energy efficient manner. Basically, the nodes depends on the sensors. So our focus will be on how the underwater sensors are working. The base station, a master node, virtually large computer data is compiled and processed with. Gives instructions about the type of phenomena to be sensed and collects results. The human operator sends commands and receives responses through the base station. So this is the overview of wireless sensor network. So let us now focus on some of the existing systems. A sensor network capable of detecting an oceanic earthquake and an impending tsunami is feasible, but must be backed by an excellent communication infrastructure. The devastating death toll and damage caused by the tsunami in 2004 had prompted urgent call for an early warning system. European Union funded project Distant Early Warning System DECE has aims at developing tsunami early warning system for Indonesia and has been quite successful. The project detects and analyzes seismic events in the Indian Ocean, the rapid assessment of their potential to unleash a tsunami, and warning at risk countries by means of network of detectors made up of broadband seismometers, land and open surface based GPS instruments, tide gauge, and ocean bottom pressure and control device. Using satellite, the data obtained by these instruments is sent to a central station in Jakarta for processing. There is another system known as INCOIS, Tsunami Early Warning Center, is a part of Indian Nation Center for Ocean Information Services. It has a warehouse of ocean related information gathered from institutions in India involved in marine data, ocean observation, and atmospheric sciences.
Hello, Prashant sir, are you there, sir?
I think there was a problem. I'm back now.
Okay, okay.
Okay, there was a network problem. I'm so sorry.
Okay, no problem.
INCOIS basically is the Tsunami Early Warning Center. It's a part of Indian Nation Center for Ocean Information Service. It has a warehouse of ocean related information gathered from institutions in India involved in marine data, ocean observation, and atmospheric sciences. INCOIS translate it into deliverable products to a range of users: fishing community, state fishery department officers, planning commission, shipping industry, navy, coast guards, pollution control board, etc. for timely dissemination of advisories
following a standard operating procedure. Seismic and sea level data are continuously monitored in the warning center using a DECE software application that generates alerts in the warning center wherever a preset threshold is crossed. The software enables operations, display of location of seismic sensors, tide gauge, bottom pressure sensors, retrieve real-time data, online plotting, overlay tsunami travel times by picking up the right scenario from the database, warning generation and decimation. This is the diagram, block diagram, in fact, of the INCOI system. You can see in the lower part, bottom pressure recorders in the tsunami-genic zones are there. A network of land-based seismic stations. Tide gauge network is there in real time. Upper ocean surface met ocean observation, radar-based coastal monitoring stations. All these collect information and sends it to the data communication system over the INSAT. And from there, numerical modeling and history data are used to generate the warning if needed. There's another system which is very popular. It is the DART. It is Deep Ocean Assessment and Report Sonar System. Okay, it is basically a German system, an early warning system for tsunami in operation in Pacific Ocean, and consists of a network of seismograph and tidal gauge linked via satellite to monitoring centers based in Alaska, USA, and Hawaii. DART use deep sea pressure detectors that measure changes in water depth as a tsunami wave passes over it. The sensor then transfer the information to a surface buoy, which relays it to the monitoring stations by satellite. DART is also less vulnerable to earthquake damages than tide gauges, but experts insist that multiple detection systems are essential. This is the diagram for DART. As you can see, there are bottom pressure recorders, which are basically sensors, and they are connected. But this system is having a drawback that the number of sensors is limited and fixed. There's another very popular system, which is the German-Indonesian project known as GITEWS. It was started again in 2004, developed a GPS-based component for detection of post-seismic land mass movement and tsunami waves on the ocean. It covers station design, data transfer, near real-time data processing, and warning center operator desk. The project detects and analyzes seismic events in the Indian Ocean and issues warnings by means of networks of detectors made up of broadband seismometers, land and ocean surface-based GPS instruments, tide gauge, and ocean bottom pressure control devices. Using satellite, the data obtained by these instruments is sent to a central station in Jakarta for processing and further warning generation. This is the diagram for it. You can see there are more number of sensors compared to the previous ones, but still the sensors are limited to a few places, and to believe the earthquake or landslide undersea can occur at any place. So again, this system is also not very good. So what are the flaws in these existing systems? 90% is a tsunami generated by an earthquake, but also volcanic eruptions and landslides may be the triggering events. The early warning part of tsunami hazard management till date relies upon the measurement of sea level and computer models to characterize the tsunami waves. Scientists rely on ocean-based buoys and models to track and predict the path of a tsunami. Geospatial technology has immensely helped in the design of early warning system for tsunami. The observation need to be made at the site and not at the sea level is the most important point here. So we need to put the sensors at the site. Our contribution. Sensor networks that measure seismic activity from remote location can provide tsunami warning to coastal areas or study the effect of submarine earthquakes. Underwater sensor networks have the potential to pave the way for unexplored applications and to help observe
and predict the ocean. We combine the underwater acoustic sensor network with satellite and terrestrial communication systems together with the internet to generate early warning. This type of underwater acoustic sensor network technology integrated with the internet technology would make the data and warning accessible to one and all. So we now focus on underwater sensor network based early warning system. Nodes are spread over the entire ocean bed under coverage. It has space-based monitoring with satellite technology in addition to other terrestrial communication technologies. There are 3 levels in the design. The first level deals with communication inside the harsh underwater environment where only acoustic communication is possible. The sensor nodes are organized in clusters and these nodes communicate over short distances while the cluster heads convey the data collected to the surface stations closest to them. In the second level, the surface station collects the information and forwards it to the coastal data collection center through line of sight microwave terrestrial transmission. There may be a master surface station which is more capable in terms of power and communication. In the third level, the information is either directly sent to a universal data collection center through satellite by the surface station or the coastal data center. This is the diagram which explains the thing. We have in situ sensor network underwater, early warning system front end, and early warning system back end, and intercommunication using satellite and internet. Challenges in implementation. Power and energy optimization are essential, especially critical for underwater sensor network. Acoustic communication will consume more energy than RF channels, and energy harvesting is much more difficult because solar and wind energy are not available. Since underwater acoustic networks are battery operated, lowering the transmission power may extend the network life, but the cost of increased bit error rate, as signal to noise ratio might not be high enough to ensure satisfactory information transmission. Motivated by these constraints, underwater acoustic networks design require low power consuming sensors, good bit error rate system with least complexity. The challenges in implementation. Doppler spread depends on the ocean environment, chemical, physical properties of the water medium such as temperature under consideration and varies from ocean to ocean. These variations together with the waveguide nature of the channel cause the acoustic channel to be temporarily and spatially variable. Routing techniques. A common practice used in terrestrial sensor network application is to design routing algorithms that minimize the communication power and consequently increase the sensor lifetime. This requirement needs to be ported to underwater as well as space applications. Modulation schemes. Among the important design parameters are bit error rate, peak to average power ratio, number of subcarriers, signal bandwidth, block duration, guard intervals, subcarrier spacing, pilot carriers, and null subcarriers. Now, what are the performance metrics? The system will be judged by the reliability, correct and prompt warning, so that public can be targeted, warned, and evacuation measures can be initiated. State-of-art ocean instrumentation. Instruments are installed on the coast, in the ocean, or on the ocean floor, measuring the sea level fluctuations, both on the ocean as well as on the coast. Analysis of different measurements at a very early stage with the help of seismometers, GPS instruments, tide gauge, and buoys, as well as ocean bottom pressure sensors. The recording and analysis of bathymetric data for determining the topography of the ocean floor is an essential basis for modeling. Warning centers. Here, the data of the particular sensor system are received and analyzed by means of decision support system and on simulation and pre-tailored hazards. Messages, early warning generated messages have to be delivered to governmental institutions, local disaster management, action forces, and media. The conclusion of this whole finding is that the development of early warning generation system based on sensor network will undoubtedly contribute to save a lot of human lives facing natural disasters. It can be concluded that reliable communication, low power design, and efficient resource management will remain the major challenges of underwater sensor network based early warning generation system. Sensor waves for early warning will prove to be a powerful technology for environmental and ecological research, in addition to saving human lives. However, in deploying such a system, it should be taken care that the aquatic ecology balance is not disturbed. Now we'll talk about some of the underwater sensors. A very popular underwater sensor is Aqua. It employs 4 hydrophones, multi-channel receiving and omnidirectional transduction. It can be used at a depth of 200 meters. Its range of communication is over 5 kilometers. And it has transducers which include omnidirectional, outstanding, vertical and horizontal or slant range shallow water performance. Underwater sensors that is very popular is the Oxynor. It consists of phase detection board for luminescence detections integrated in 12 mm stainless steel fitting. Features include simple integration, low power consumption, luminescence lifetime detection via a precision phase detection board. No oxygen consumption. Measure in any position, also vertical and upside down. So basically these sensors are widely used in the underwater sensor networks, and their performance is very important because the power consumed by them and the quality of signal output is very important, because we have to communicate that data to a remote location using the underwater sensor network. This is an example which is a very large size sensor node basically, which is known as fetch. This is ambient zero ambient. This is known as AZA. It's a long life subsea sensor logging node that enables data to be wirelessly extracted via its integrated high-speed acoustic modem. So what you are seeing is actually not just a sensor, it is an underwater acoustic modem. This high-quality pressure sensor fetch is compatible with Sonar Dyne's ultra-short baseline. USBL is mainly used in positioning system in submarines and ships. This is LI 192. It uses a silicon photodiode and a glass optical filter to create nearly uniform sensitivity to light between 400 and 700 nanometer, which closely corresponds to light used by most terrestrial and aquatic plants and algae. So this is used in detecting ecological observations. AP7000 probe comes with optical DO, conductivity, pH, ORpH, temperature, depth probe. It has 6 customizable sensor ports allowing you to record up to 16 parameters at once. Wiper clean all the sensors that are connected to the probe, keeping the sensors cleaner for longer life. Alpha series pH sensors are low-cost, consistent performance sensors. They have high-quality double-junction pH electrode, operate in environment from 0 degree to 110 degrees, provided with integral low-noise semiconductor cables. Teflon annular junction for broad application capabilities. Compatibility. Tough right-on body material can withstand up to demanding applications. Solution ground option to help electrically noisy applications. The Aqua sensor RDO Pro is an optical dissolved oxygen sensor for wastewater monitoring. Connect this advanced sensor directly to a PLC for seamless integration with industry control system. Basically, this type of sensor is used in water treatment plants. 0 to 20 ppm measurement range, no membrane, only annual field replacement caps is there, high precision and accuracy with fast stable response, no conditioning necessary prior to use, fast startup, reduced maintenance, long lasting calibration, resist photo bleaching and abrasive process media. This is simply a plug and play system. The Analog Plus is a dissolved ozone sensor, uses 3 electrode holographic Clark cell technology to work continuously in the most challenging industrial applications. Holographic sensor designed for continuous use in most demanding industrial applications, replacement membrane caps for longer life, and it has a range of 0 to 40 ppm measurement and 0.01 ppm resolution. ppm basically is parts per million. The Aqua measures are very widely used in Internet of Underwater Things. These are fish tags and receivers. They are broad scale movement monitoring, fishery research sensors. They can be used in ecosystem and habitat monitoring. They have very fine scale movement and they can be used for human impacts. The Tourmaline ICP is basically a piezoelectric sensor to measure shock waves and bubble energy associated with underwater explosion testing. There are certain sensors we are used to monitor the underwater plant life, like how the planktons, how the coral reefs are performing, what is the problem of pollution in close to these coastal reefs, and so on. Real-time environment data measurement can be done, like dissolved oxygen can be measured, salinity, chlorophyll, blue-green algae, turbidity, color dissolved organic matter, etc. can be monitored with these sensors. There's another very interesting thing, that optical fiber cables, which are placed basically for communication system, can also be used as sensors. The ocean floor is crisscrossed by over 1.2 million kilometers of optical fiber cable. 41-kilometer long cable deployed off the coast of France to retrieve data from sensors of MEUST Numer N, an underwater observatory that comprises a neutrino telescope and sensor dedicated to the Earth and environmental science at a depth of 2,500 meters. The point here is that there is a network of optical fiber and people can use that network to monitor the sea floor. And so the optical fiber can be used as a sensor. Small impurities in the optical fibers send parts of the light they carry back to the transmitter. By stretching or contracting the fiber, the passage of a seismic or acoustic wave alters the distance between these impurities, and thus the backscattered signal by a tiny amount, about a nanometer. By injecting pulses of light into an optical fiber and then analyzing the backscattered signal, the team converted the 41-kilometer optical fiber into more than 6,000 seismic sensors. An earthquake of 1.9 magnitude that occurred during the trial was detected at over 100 kilometers from the cable. So the already existing optical fiber network on the sea or close to the seafloor can also be used for detecting seismic and acoustic activities. Now, here I will break and show you 2 videos which will show how underwater acoustic needs sensors and how they can be widely used.
In Western Norway, scientists are testing autonomous devices that can detect and understand what is happening underwater.
Inside we have like electronics for sensing and also for processing. That means we can do some local processing, like if we want to detect the ship or where is a leakage of the oil pipe, we can just do everything here, and then this one will send the signal to the control center or central station.
Gas bubbles may be a symptom of a failing pipeline. A sensor node recognizes the sound of bubbles and alerts engineers to a possible leak. But would it work on a large scale, deep in the oceans? A European research project aims to build a functioning network for acoustic surveillance.
Positions underwater sensor devices. They go into the water, deep into the water, and they monitor the environment. And if they see anything which is wrong, they will communicate with each other and then raise an alarm if needed to the shore.
A number of specially developed sensor nodes are placed hundreds of meters down on the seabed at a distance from each other. Each unit is completely autonomous. They have a built-in battery, so there is no need for a power cable, meaning deployment is far cheaper.
This device is a big device. It's a device intended for deep water, up to a few kilometers deep. You can see it on packaging, casing, and also on the electronics. So also intended for high reliability, so high range, high throughput, and high quality.
The nodes can talk to each other using acoustic signals. In the control room on board ship, computer engineers are monitoring the speed of a coded message being communicated between the nodes through the whole underwater network.
Il concetto importante è che qui si parla. That's the important concept of this network. You don't just do point-to-point communication. Instead, all devices in the network cooperate to accomplish challenging tasks. Like here, we have several devices that aren't able to talk to each other directly, but they collaborate in order to deliver the information to the central control station monitoring the network.
Once an underwater sensor detects a leak, it transmits the coordinates using sound waves. Other nodes receive and then retransmit the signal, so passing it along the chain of beacons. To access the network from the surface, researchers use floating communication buoys that convert acoustic messages into radio signals.
Yes. You can now hear actually the acoustic modem sending signals towards the seabed in order to, it can actually ask the seabed nodes what is your current status, and it sends back information. The reason why we are using acoustic signals in the seabed is because electromagnetic waves do not propagate well in salt water.
In the future, acoustic networks could be used for many tasks such as underwater navigation, tracking sea animals, or protecting oil pipelines and drilling platforms from accidents.
The system can potentially make the world much more safer, environmental friendly, so we can detect any event. So, for example, the BP oil spill some time ago, it could have been prevented.
Research is continuing to improve the reliability and efficiency of the underwater surveillance system.
As you have seen, that underwater acoustic communication involves that type of modem, sensors, and the most important thing is that it's very difficult to place those sensors. Those sensors should be able to tolerate the harsh underwater environment. I have another very important thing which shows how the sensors are designed for underwater environment. you have seen how a powerless sensing system can be designed in which reflection is directly used. So now I move to the last part of my presentation, which is Internet of Underwater Things. You know, Internet of Things is very popular, and it fully depends on sensors. In the same way, Internet of Underwater Things also depends on sensors, but the problem here is that these sensors have to work underwater. So very quickly, I'll just touch this topic. Why Internet of Underwater Things is needed? The current count of IoT devices is 30 billion, excluding phones, tablets, and computers. Ambitious terrestrial initiatives like Google's Project Loon and Facebook's Aquila drone are trying to digitally connect every rural and remote corner of the land. We are missing out on connecting underwater. Oceans and lakes cover 71% of the Earth's surface and support the life of nearly half of all species on Earth. What are the characteristics of Internet of Underwater Things? IOUT has similar structure and function as IoT, but restricted by the computation and energy limitations of the device. Here we have a different communication technology. Most communication in IoT are based on acoustic links. Different tracking technologies. IoT uses radio RFID tags, but here IOUT usually fishes are tracked with different technologies depending on the fish size and species, type of data to be collected, and habitat utilization. Acoustic tags are sound emitting devices. They have large detection ranges up to 1 kilometer in fresh water and are used to track fish in 3D. Radio tags transmit a RF signal detectable through a system of one or more antennas and receivers. Limited range up to 10 meters in fresh water and cannot work in the seawater. Passive integrated transponders, PIT tags, are glass encapsulated implantable RFID devices. They require an external energy source to activate the tag for data retrieval. They have a limited detection range and perform poorly in seawater. However, they do not depend on batteries and can be implanted in small fish due to their limited size. IOUT architecture has 3 layers. The perception layer, which is the most important one from sensor point of view. It identifies objects and gathers information. It is formed mainly by underwater sensors, underwater vehicles, surface stations, monitoring stations, data storage tags, maybe audio, radio, or PIT tags, and hydrophones, receivers, and tag readers. The second layer is the network layer. It consists of a converged network made up of wired, wireless, privately owned networks, internet, network administration system, cloud computing platforms, etc. It processes and transmits the information obtained from the perception layer. It enables the access of the source surface station over the sea to the radio channel to process and transmit the required information obtained from the perception layer. This information is retransmitted to the onshore command center using a satellite communication. General packet radio switching system, GPA, or CDMA system, wide CDMA system are used. The application layer, which is the layer of great interest to the user, it is a set of intelligent solutions that apply to the IOUT technology to satisfy the needs of the user. The Web of Things is a vision where smart objects are integrated with the web. The smart objects application can be built on top of representational state transfer REST architecture. The REST architecture style decouples applications from the services they provide, which can be shared and reused. The application scenario of IOUT. One of the example is the aquarium, and fish tagging in aquarium with PIT tags using RFID enables that visitors learn fish characteristic in real time. The tag reader located out the exhibition tank emits radio waves. Every time a tagged fish swims within range of a reader, it sends its unique identifier string towards the reader, which forwards it to the RFID server. User can also detect this ID with the aid of a reader embedded in a monitoring station or a smartphone. Fish specific information is returned to the RFID database to the touch screen of a computer next to the aquarium. The species name, origin, diet, and other individual characteristics of the fish like age, weight, etc. are displayed as user navigate through the menus. Instructive videos can also be stored and downloaded from a multimedia server. This system is also an accurate way for aquarium keepers to track the individual medical history and treatment record of every fish in the tank. Imagine a very large aquarium where visitors come and they just see the fish, they do not get any information about the fish. But this will be an interacting aquarium. Whenever a fish will approach you, the screen will display details of that fish and you will get the information about a particular fish. And again, when the fish goes and a new fish comes, you will again get information about the new fish. So it will be a very interesting and interactive system. In this diagram, the whole thing is depicted in a single diagram. You can see there is an aquarium. When the fish will approach the audience will get proper information about the fish. When the fish will go and a new fish will come, again the information about the new fish will be available. So this will be a kind of interactive multimedia aquarium system. And you don't need any guide for guiding you and telling you about different fishes. Then it can be used in pipeline monitoring. Underwater sensors and AUVs integrate for an efficient inspection of marine infrastructure, example for control and detection of oil spills at pipelines. Harbor security. Underwater sensor networks together with underwater and surface vehicle can contribute to protect harbors. The mobile security network is formed by autonomous sailing vehicles, autonomous underwater vehicles, airplanes, and satellites. Stationary platforms that contain buoys and sea-mounted equipments are also included. A large variety of sensors can be mounted on the vehicles. I'll just show you a very small video for this. Suppose there is a oil leakage at one point in an underwater pipeline. It is detected by a nearby sensor node and this message is conveyed over the sensor cluster system to a moving vehicle which is there to detect such spillage of oil or pipe breakage. The vehicle will now approach the site. It will now inspect the leakage and send information to the concerned engineers or the maintainers. So you have seen how this type of a network will be very useful. So we now conclude this whole thing. Like the early days of information technology, IOUT is currently in the R&D phase, driven by state-funded organizations. And soon, once the communication between underwater things is technically stable and the software architecture established, a new kind of Wi-Fi is helping to keep you up to date of underwater news. detecting early signs of tsunamis, monitoring the health of animals, surveying shipwrecks and crashes, establishing interactive real-time aquatic education, ecological monitoring applications, and archaeological expeditions. These are some of the references, and I'm now open to any question related to underwater sensors, underwater acoustic sensor network, and underwater sensing technology. You can ask me questions. I'm here to answer.
Thank you, sir. Hello.
Yes.
Yeah, thank you, sir, for your nice presentation. Now I will ask all the participants whomsoever is having any query, they can they can feel free to ask with sir.
Good afternoon, sir.
Yes.
Sir, for underwater, how we can do the data storage and the retrieval, sir?
Actually, the underwater nodes are mainly having a very small amount of power and computation capability. The aim of those nodes is that they have to extract the measured quantity and transmit it. So they have a very low storage and computation capability. So they have to transfer the data to their nearest node, and ultimately that is to be transmitted to the host data collecting center. Okay. So they have very small amount of memory because they are all battery backed and they are submerged in water. It's very difficult to give large amount of continuous power to them. And if you use a lot of battery, your node will get exhausted. So the main idea is you have to do underwater acoustic communication, read and transmit.
Okay, sir. Thank you.
Hello. Sir, good afternoon, sir.
Yes.
Sir, this is Vinod Kumar from Coimbatore, sir. So that was a nice presentation, sir. I have some questions. I'm also working on underwater sensor technology. I just registered for my PhD also, sir. So my question is, actually I plan to work on wireless networks in underwater. Okay, so I'm just planning to work on this one, routing protocols under the water.
Okay.
Can you give me some tips or some suggestions related to it?
Yes, there are some very good surveys. You can refer one of the survey by ATAL. Okay.
Sir.
In which they talk about all the popular routing algorithms.
Okay.
And different techniques that are used underwater. Okay. So
okay,
have a good look at that.
Okay. Okay. So then, whether we are using actually what you have explained is we have sensors which is deployed under the water. So whether is there any sensor technology which without anchoring the sensors, that is sensor is not fixed at one place.
Some of the sensors keep on floating. Okay.
Okay.
Some of the sensors keep on floating, and their job is to collect the information from the sensor nodes and convey it to the surface buoys. And these movable nodes, they have the capability that they can get connected to the surface buoy and again get charged and again go back to the respective field. Okay. But remember, these surface buoys, they suffer from the problem of Doppler spread. Okay. So when you are designing these underwater vehicles, you have to take care of underwater Doppler effect. Okay, which is very prominent in this case.
Okay. Sir, is there any, can you suggest me any software related to networks underwater?
Actually, there are no standard softwares, but different companies, different universities have their own softwares. One very common software is developed by WHOIS, Woodhull Institution of Oceanography. Okay.
So can you please repeat that?
Woodhull Institute of Oceanography.
Okay.
So they have a software in which you can just connect the sensors and it will help you establish a full-fledged network, underwater network.
Is there any protocol system?
Actually, see, in underwater communication, the protocols are still in the making phase. There are no standards for underwater acoustic communication like we have for wireless communication. But some universities have come with de facto temporary protocols, and there is no interoperability right now existing for underwater communication systems.
In the underwater sensor, the viscosity, the viscous drag, that also taken into account. How to sense that?
I'm sorry, could you repeat?
May be vary from depending upon in underwater sensor. In case of underwater sensor, the depending upon the sea water or river water or whatever may be, the viscous drag that also changes. That vary.
Yes, the point is, I got your point. See, basically the underwater composition, it may be seawater, it may be a river, or it may be fresh water, varies from place to place. Okay. So whenever you have to make a system, you have to first study.
In seawater, the pH value is something. In case of river,
my point is that if you want to make a system particular to a particular place, specific to a particular place, you have to do the study, find out what is the absorption, what is the pH, what is the temperature, what is the amount of impurity in it in terms of ppm, and then you have to design the system. Suppose you are working in a very saline sea, then there will be more absorption. So you have to keep the power, transmitter power very high, so your batteries will get discharged very quickly. But if you are working in clear water, then the power level will be low and your lifetime will be longer. So it depends on the type of water you are working in.
Okay. Now, ultrasonic sensor, can it be possible?
Yeah.
In case, by using ultrasonic sensor, is it possible to avoid these types of variation, fluctuation?
Actually, underwater communication takes place with ultrasonic sound only. Generally, we use a frequency from 6 kilohertz to 40 kilohertz. Okay, and we use this 40 kilohertz just because the absorption is low. If you use normal sound, there will be very large amount of absorption, but if you use ultrasound, the absorption will be less. Okay.
The time factor that can be changes also.
Yeah.
The time factor in case
yes,
of
time factor is also important because the sea activity keeps on varying. In the morning it may be different, in the evening it may be different. So we have to keep track of all these things. It's very difficult to communicate underwater. That is why we say that underwater is a harsh channel. Okay.
If there is any software developed so far for that?
I told you there are some softwares by some different universities. Like Woodhole has got its own software, Stanford has got its own software. Okay, so different universities have their own domain of study and have developed certain softwares for themselves. Okay. But it's not publicly open. Like we have wireless standards, we do not have standards in softwares.
Okay. Sir, I have one question if you allow me to ask.
Yes, yes.
Yes, thank you, sir. First of all, I would like to say that the presentation and the videos were very informative, and we enjoyed this session very much. Sir, in case of underwater communication, the transmitter and the receivers which are used, they might be spreading that acoustic waves in a particular direction through beaming, or it can spread that signal to in a spherical manner to all direction.
Okay, I got your question. See, the point is that the underwater nodes do very short range communication. Okay, the network has got nodes close to each other, and so they have to do very short distance communication. Let us assume that the two nodes are separated by not more than 10 meters. And most of the time, these sensor nodes will generate
signal in all directional. So they are omnidirectional. Okay.
Okay, sir. And sir, one more question. Likewise, in our radio communication, there are band licensing. So for underwater communication, is there any kind of regulation for?
I told this earlier also. Like wireless communication, we do not have international standards in underwater communication. There are different groups which are working on it, and we are yet to get the accepted standards. So far we do not have standards. Although depending on the quality of underwater, like what type of sea you are, salinity and all those things, the frequency range is unique. So most of the communication is done in 6 to 40 kilohertz bandwidth. Okay. If you allow me, I'll just show one more video to conclude this session. It is
Sir, one last question. Can I?
One question more.
Sorry to disturb you.
Yes, please ask.
In case of navigation.
Yes.
How they detect the position of one expected submarine in that case?
Okay, see, basically the submarine generates certain amount of signal, okay, which is received by the receiver which is trying to locate it. Okay. Then there is a concept of RSS. RSS, received signal strength. Yeah. There's a concept of received signal strength, RSS. So the submarine would look in that direction. Okay. Suppose, like human beings, suppose you listen a sound, you turn your head that side. In the same way, the object which is supposed to detect a submarine would send a signal, receive the reflection from it. Okay. It is like the process of echoing, and it's a very old system. Sonar is being widely used over hundreds of years for navigation. Now I would just like to show a very small video, which is here.
What is really what?
Yeah. What is?
Any more question from participant side?
Sir, I have one more, sir.
Yes, please.
Let the video.
Here we have 3 boys and 6 units.
It's a nightmare scenario for any scuba diver. Being separated.
I will request all the participants to turn on their webcam.
But the new invention could put an end to that.
Here we have 3 boys and 6 units.
It's called the Underwater Information System, or UIS. Bertie Argonin is one of its creators.
Some big sensor here and works exactly like a buoy as well. It makes a connection to the DECE.
Today, Bertie plans to test the system in the waters of the Baltic Sea. He'll be joining the Nautics Sport Diver Club of Finland on a hunt for a ship that went down more than 140 years ago.
Our aim is to find a way how we can support these guys when they try to find the wreck.
It's a French from Granville. There was 9 men overall. It was a huge storm when it sunk.
The Jean Bart met its maker near the town of Turku. All 9 members survived.
The surface is covered by the oceans, and beneath those oceans we've got vast resources in terms of energy, minerals and food. We're all used to GPS technology enabling us to position ourselves anywhere on the planet, but as soon as we go below the water, that's simply not available to us. So Newcastle University's technology has really allowed that to happen. Remotely operated underwater vehicles are very commonly used for inspection tasks. So if you want to go and have a good look at something and it's too deep or too hazardous to send divers down there, then these ROVs, as they're known, are very commonly used. Divers are only able to go down to a certain depth, and beyond that we rely on robotic underwater vehicles. So communicating with these vehicles and also tracking their position is extremely important. Here at Newcastle University, we've been working for over 20 years to create new acoustic technologies that are more reliable or more capable. Our technology enables us to accurately track any vehicle or even a diver subsea. Historically, acoustic communication technology was used in high-value applications like defense and oil and gas industries. But in recent years, there have been more and more commercial products, including some that Newcastle University have helped to create. The MicroNav product was created to produce an affordable solution for small, remotely operated vehicles. This is the surface end of the system. So this is what we call our USBL array. So this device receives signals from the subsea end of the system. So this device, the transponder, is mounted on board a small vehicle or a diver, and it exchanges signals through the water with the surface unit. The surface unit can work out exactly where this device is by estimating the direction of the signals arriving, and also by measuring the distance between here and the subsea unit. There are several hundred of these MicroNav systems around the world being used today. So technology used in the MicroNav product has actually been miniaturized further and expanded in terms of its capability as part of a very ambitious project called CADI, as part of an EU consortium. The concept is to create a robotic dive assistant or dive buddy, so that rather than being reliant on another human being, the diver can be reliant on a robot or more than one robot to assist in its operation. It reduces the manpower, the number of highly trained divers that need to be in the water at any one time. The technology created and demonstrated in the EU CADI project is now being commercialized with a company called Blueprint Subsea, and that's created what we call the C-Track range of products, which again is a system for underwater communication and positioning, but very much miniaturized and capable of higher data rates than previous products. The long-term goal is to have long-term infrastructure out there in the oceans to support communication and positioning. But if we're actually going to achieve this goal, we have to do it in a way that doesn't create an environmental problem. We don't want to be emitting continuously high power acoustic signals underwater. So we're working on technologies that will actually minimize environmental impact by transmitting signals buried below the background noise, so that marine life or any of the divers out there, for example, wouldn't even be aware that these signals were present.
So thank you all of you for listening and cooperating in this session. I hand to Dr. Jayendra Kumar now.
Thank you, sir. Thank you, sir, for your kind cooperation and awareing us with such innovative technology in underwater communication and underwater sensing. So now I would like to ask everyone to kindly switch on their webcam for at least 1 minute so that I can take some pictures. Okay, thank you very much. So before leaving for our lunch break, I would like to inform all the participants that we'll be back here again by 3 o'clock. 3 o'clock, we are having a live demo by Mr. Arvind Dikshit from Advanced Technology Private Limited. This company deals with sensors and IoT solutions. So there will be a live demo. I hope you all people will enjoy. And most of the people are asking in the chat box that when this quiz 3 is going to held. So quiz number 3, which is our final quiz, will be holding from 4:30 p.m. During the validatory session. So there will be in total 20 questions. The marks will be of 25. Total marks is 25, number of questions will be 20, and related to the presentation only these questions are framed, and the link will remain open till 6 o'clock, but you have to attend the quiz within half an hour. So time allotted is half an hour, but the link for the quiz will be kept open up to 6 o'clock. So I hope I am clear. People who want to have